Certo, se net.
Welcome, all of you. I cannot see how many, but I assume there is a room full of people dispersed through the planet watching this Test of Time Award ceremony. It's my honor to present it. I'm Rob van Glabeek. I will start with explaining how the award works, introducing the committee members, and then go to the award giving and talks of the various award recipients. The Test of Time Award of Concur is meant to go back about 20 years back and give awards to work that really stood the test of time and is still relevant today. We didn't expect the best papers to be uniformly distributed and therefore do not go exactly 20 years back every year, but arrange over an interval. So in 2024, the first regular award happens. It will happen every 2 years and go to a 4-year interval that is 20 to 17 years before that Concur where the prize is given. So every time there is a 2-year overlap in the window where the prizes will be awarded. In the 4 years from 20 to 24, we try to catch up by doing not once every 2 years an award, but 2 awards, 2 award packages twice for every Concur until we are caught up with the time. And every award might be 1 or 2 papers over a 4-year period. And this year there are 4 papers that will get the award. We are dealing with the periods 94 to 97 and 96 to 99. The committee this year consisted of Nathalie Bertrand, Luca de Alfaro, Katusha Palamidesi, Nobuko Yoshida, and myself. And we have selected out of many, many good contributions, first of all, in the period 94 to 97, 2 papers, and I will do them one by one, and at every time first deal with the talk of that paper and then go to the next one. The first paper was by David Janin, Ivan Walukiewicz on the expressive completeness of the propositional mu calculus with respect to monadic second-order logic. I will tell you why we gave this award. This seminal paper relates the expressive power of monadic second-order logic and the mu calculus, showing that the bisimulation closed formulas of monadic second-order logic are equivalent to the mu calculus. This, we believe, is a very deep and insightful result, providing a contribution to the foundational nature of the field of logic and computation. This insight was one of the central factors contributing to the role of the mu calculus in model checking, where it provides the computational counterpart to logics for expressing system properties. The relation between logics and the mu calculus, which can in great part be traced to this paper, has been extremely fruitful one, with implications in algorithms for the verification and analysis of transition systems, probabilistic systems, time systems, games, and more. I will now give the floor to Igor, who will tell something about this paper and its impact. Go ahead.
Thank you very much, and thanks a lot for these very kind words. I try to share the screen now. Up. Does it work?
Yeah.
Yeah.
Yes.
Okay. So we are, of course, delighted to receive this distinction for our work. This is result from 25 years ago. And it's a lot about trees, and of course it's about mu calculus, and it says that mu calculus in some sense the best program logic possible if you stay in the world of monadic second-order logic. And this is quite satisfying because mu calculus has both good syntax and very clean semantics. So more precisely, the result says that every property that can be written in monadic second-order logic of transition systems, and that is by simulation invariant, can be expressed as the mu calculus formula. And if you think of monadic second order logic as a yardstick for the expressive power, it's indeed very powerful logic over transition systems. And you think that the properties you want to talk about are behavioral, this means more or less that are by simulation invariant, then this result says that in some sense, mu calculus is the best you can aim for if expressive power is considered. So in the rest of this talk, I will quickly give you some background for this result, explain more about it, and then some follow-ups later. So first, monadic second order logic. Transition systems are just graphs with nodes that are called states and edges that are usually labeled, but I will not draw them on the labels on the pictures. And monadic second order logic is just first order logic extended with quantification over sets. So we have this quantifier that exists capital Z, where Z ranges not over nodes, but over sets of nodes. And then we have atomic predicates like X belongs to Z, meaning that a node X belongs to a set of nodes Z, and an atomic predicate for transition relation. There is an edge from X to Y. With this logic, you can express a lot in transition systems, and especially you can say that the transition system is a grid, and then with the existential universal quantification of sets, you can play with colorings of nodes in the grid. And because of this logic of the transition systems is highly unmanageable. So it's in analytic hierarchy, the satisfiability of this logic. It means that you cannot have neither a proof system nor semi-decision procedure. It's very difficult to deal with this logic of a transition system. In the seminal work, beginning of the 60s, Bucci showed that if you restrict to a infinite sequence, then monadic second order logic becomes decidable. And for this, he used automata approach that we now call Bucci automata. And 7 years later, Rabin extended this approach to prove decidability of monadic second order logic of a binary tree. And this is a very strong logical system. Up to date, it's one of the the strongest decidable logics. Later, once again, 6-7 years later, Stupp has shown decidability of monadic second order logic over 3 iterated structures. This is an interesting construction where instead of a node having just 2 children, it has a fixed structure of children, that is the fixed number of children connected in some way, related in some way between them. So for example, these children can be put into a chain or into a tree, etc. And he showed that if monadic second order logic of theory of a structure of these children is decidable, then this iterated structure where we copy this basic structure in a tree-like fashion, the monadic second order theory of this iterated structure is still decided. So this was a next step beyond trees, and the really next step was given by Mushnik, who also considered a clone relation. So he considered the same structure as before, but added a clone relation that was saying that a node in the child structure is the same as the node in the parent structure. And this is a really powerful operation that has many connections. It's a backbone for push-down hierarchy. It also has connections with evaluation in the lambda calculus. So it's a surprisingly powerful operation. And once again, the monadic second order theory of this iterated structure is decidable once these gray bubbles have decidable monadic theory. So this is on the part of monadic logic, what happened before our result. And we understood more and more what happens with more complicated structures. On the mu calculus side, there were also good advances. So the logic was proposed by Koze in 1983, and it's just a modal logic together with the fixed point operator. Then some years later, 5 years later, Emerson and Jatla has shown that this logic is decidable in X time. And here already they introduced a lot of automata theoretic machinery to solve this problem. The model checking problem is still really an open problem. So it's in NP and there is constant progress on this problem, but we still don't know whether it's NP. And then also in 98, Damian Niewinski has shown connection between mu-calculus and parity automata and MSL, monadic second-order logic. So he has shown that on binary trees, the three things are the same. And what interests us here is what happens in general transition systems. So it's exactly the question of Niewinski, but on general transition system. Now, to answer this question, we need to understand what is bisimulation invariance. So consider this transition system with one node. There's one node and a self loop. This node is bisimilar to any node in this infinite chain. Yes, because this node can do infinitely many arrows, and any of this nodes can do infinitely many arrows. And it's the same in this tree. So this node in the original transition system is bisimilar to every node in this tree. Okay, so the property is bisimulation invariant when it cannot tell the difference between two nodes that are bisimilar. So in this case, the bisimulation invariant property would not tell the difference between the node in the original system, any node in this chain, or any node in this tree. In particular, it means it cannot count the number of successors that are the same subtleties. And this is the intuition behind our result. So the result says that if you have monadic second order property and it's bisimulation invariant, then you can write an equivalent mu-calculus formula. There was a similar result before for the first order logic that inspired us a lot. This was a result of Van Betten from 83, who shown that first order logic property that is bisimulation invariant is equivalent to the modal logic formula. And once again, the idea is that first order logic can make the distinction between this structure on the left and on the right. It can count the number of successors, but once we say that the property is bisimulation invariant, it cannot. But the techniques in these two results are very different, because in the case of first order logic, you can do compactness kind of arguments that are not possible for monadic second order logic because it's so expressive. So that's the way to prove it was to understand the power of monadic second order logic on trees with unbounded branching in terms of automata. Do the same for the mu-calculus, and then compare these two models and do some relatively simple, finally, pumping arguments and obtain this result here. So what are the consequences of this result? First, it says that mu-calculus in some sense expressively complete. So if you take a program logic, meaning logic that is bisimulation invariant, and this logic lives inside monadic second order logic, then it is not more expressive than the mu-calculus. So in some sense, mu-calculus is the best we can do. Moreover, as I have said before, MS-SOL is not decidable logic, and it's not decidable if a formula of monadic second order logic is bisimulation invariant. So mu-calculus gives a decidable syntax for something that is not decidable inside of monadic second order logic. And what happened after this result? Well, David with Giacomo Lenzi studied fragments of mu-calculus and fragments of monadic second order logic and shown the correspondence. So for example, monadic second order logic with just one string of existential quantifiers is equivalent to formulas with just the greatest fixed points. With alternation quantifiers, it's bisimulation invariant fragments equivalent to alternation of greatest and least fixed points. Müller and Rabinovich have shown kind of similar result, but for CTL star. So here the corresponding logic is monadic second order logic, but restricted to path quantifiers. And of course, once again, is bisimulation invariant fragment. The same techniques or technology was used to show interpolation property for the mu calculus by D'Agostino and Hollenberg. And the same techniques in spirit were used then to analyze guarded fixed point logics to show decidability and some model properties, and many other fragments up to guarded negation logic, which is probably the strongest logic in the whole family of things that happen here. And at each time, it's the pattern is kind of the same. So we have an automata theoretic method behind. We have rich local behavior, like you've seen in this gray bubble in the 3 iteration. But globally, the behavior is simple. It's a 3 automata. Okay, so I think I have given you a short overview of before, the result, and after. And it's time to thank you for your attention. Thank you.
Thank you very much indeed. That was a very wonderful expose. There is room for people in the audience to ask questions if you want. You can raise your hand or type anything if you didn't do that in the Q&A box that is at the bottom of your screen. Or in the chat. I see that there is something happening in the chat. Ah, great talk, yes. So the questions that I had, you have actually answered very well in this expose.
There is a question by Luke.
Yes.
There. Please ask.
Is
shall
there
I
anything
read it?
no? Yeah, I can read it. Is anything known
Yeah,
about graded mu calculus? I don't know. Not to my knowledge. No, sorry, the answer will be short. I don't know.
I wonder if there are variants that are a bit like a mu calculus or a temporal logic that go beyond monadic second order logic in some way.
These things, the guarded fixed point logic and guarded negation fixed point logic go beyond, but maybe it's not. And you get the equivalence with something. Mm-hmm. So you see, with guarded fixed point logic, you can have relations of bigger arity of which you can take fixed points, and this is what you cannot do in the mu calculus.
Aha, and you cannot do it in monadic second order logic either.
No, you cannot do in monadic second order logic either. So this is very this is more in this sense. There were interesting questions about what happens if you consider structures of special form. In a sense, for example, your transition systems are transitive. When there are many things collapse, so the fixed point formulas become trivial. Or this was another way of. But there is, for example, a strange logic that is still decidable. What you take mu calculus and, for example, you add a predicate, there is a loop transition from a state, which becomes the logic becomes not by simulation invariant, because having a loop is not by simulation invariant property, but it's still decidable, and it has many similar properties as the mu calculus. I don't think this track was very much followed of adding small things.
Yeah.
Then there is XPath, of course, the whole things with data where This is another word.
Yeah,
where
that would
it's
be an author.
mostly guarded. Yeah, it's in between. There's a long story would be there.
Thank you very much.
Thanks.
I think it's time to move to the next award, also time-wise. At the very end of the ceremony, if there are a few minutes left, people can still ask questions to all 4 award-winning paper authors. Thank you very much. Then I will mention the second award, which is given to the paper by Uwe Nesman and Benjamin Pierce, Decoding Choice Encodings. That paper makes major strides in the study of the expressiveness of process calculi. It shows that in a completely distributed and asynchronous setting, input-guided choice can be simulated by parallel composition. More precisely, the paper constructs a fully distributed and divergence-free encoding from the input choice pi calculus into an asynchronous pi calculus. The correctness of that encoding is demonstrated by establishing a semantic equivalence between a process and its encoding, thereby satisfying and strengthening the common quality criteria at that time of full abstraction. A semantic equivalence, as semantic equivalence, it employs the asynchronous version of coupled simulation and eliminates the surprising versatility of that notion by showing how it avoids the introduction of divergence in the encoding, which would be needed when using weak pi simulation. That work formalizes ideas stemming from programming languages like PIC, and it has been very influential in the area of expressiveness in concurrency. Uwe, your turn to say something about his work.
Yeah, thank you, Rob. I just noticed that what you told us is pretty much what this talk will be about. So it's in a sense congruent. So let's see. To share this. So now it should be there. So actually, Benjamin and I, we did this preparation together, and it was his share to spend the first 3 minutes. Unfortunately, on short notice, he cannot be here, so I'm trying to weekly simulate him, which is very hard, and I will not manage. So 25 years after Concur 96, this is when we had this paper accepted. And fun fact, there was a special issue of Concur 96 and we were not invited to actually submit our long version to it. What you see down here, thanks Nobuko for the interview that you conducted with us. This is how she greeted us in her office in typical Nobuko style. So I start with a quote by Robin Milner. It's from his Turing Award lecture in '93. And I mean, Milner, right? CCS, pi calculus, he was always about foundational models for concurrency. And he said that he rejects the idea that there can be a unique conceptual model or just one preferred formalism for something as complicated and large as concurrent computation. And this is pretty much about one such preferred formalism, but it's not about all of concurrent computation, but more about concurrent programming and distributed programming in particular. So it's clear that, I mean, thinking about test of time, you need to position things in the right context. So the development started maybe with semaphores and petrinets. And I mean, all Concur participants should know all of these things. There was some process calculi popping up in the 80s. And at some point, people also started to actually do programming languages based on top of them, like Occam based on CSP or Erlang based on the actor model and the like. The pi calculus came rather late into the scene, and Milner's quote is around that time, before Java and Java RMI were known. Yeah, and joint calculus came later on. So at that time, when Milner's quote was actually published, Benjamin was a postdoc in Edinburgh, and David Turner, he was a PhD student in Robin Milner's group. and they had this idea and challenge and project to actually think about what kind of programming language would we get if we start programming in the pi calculus, such like in analogy people ended up having as a programming language when thinking of doing programming on top of the lambda calculus. So that is what they did, and they ended up designing PICT, this kind of programming language, and PICT is actually based on a pi calculus, but which one? And that is pretty much what one main contribution of our work is about, finding out what the real base calculus is for this kind of things. So before I tell you what this calculus is, at that time, there was a lot of discussion about what kind of choice should we put in that language? What do we need for concurrent programming, distributed programming? And if you were looking at these many papers in the 90s and the 80s, there were all kinds of different choice. Deterministic, non-deterministic, external, internal. Guarded is maybe a little bit more interesting for programming purposes because of the proximity to things like guarded commands, or nowadays session types and methods in object-oriented programming. They can all be considered as some kind of guarded choice construct. And there were even more that we're not talking about. So Benjamin and Tafe had this PICT language designed, and they ended up having no choice at all in the calculus. And they said, well, it makes the abstract machine simpler, it makes implementation simpler. Maybe we can supply choice rather as a encoding, as a library on top of that. And that is then where my work started when I visited Benjamin in the beginning of the 90s. So the calculus is about asynchronous message passing, which deviated from the standard pi calculus back then. It's name passing, obviously. It has a form of replicated input instead of full recursion. It has no matching, and actually it is a typed calculus from the beginning, but we're not talking about types today. And this is what the PICT syntax then looked like for the base calculus, just 5 constructs. So this is PICT in a sense. And now I will try to make you understand how it is actually natural to come up with a choice encoding for something that you limit to input guards. And I make this example based on 2 branches. Both are input guarded, receiving on channel B and A something and then continuing. If you want to implement that and you have such a tiny base calculus, the only thing you have at hand is parallel composition. That's the only binary operator that you can use in order to do that. Okay, so if you put the branches in parallel, that's fine. You need to make sure that only one of them can succeed. So we need a mutex protocol kind of surrounding it. And in the pi calculus, we can implement that by having a message that plays the role of a lock. And the green true sign basically tells you the state of the lock, which means the choice is not yet decided when you have top on that lock channel. Okay, cool. So in order to decide for a choice, you basically need to take 2 things. You need to receive a message and you need to take the lock. Ideally, you would be able to do that in one go, but that is a joint input thing that you would have in the joint calculus, but not here. So we cannot do that. So we need to take these 2 messages in some order. And there are only 2 orders that we can choose. And we are going to look at both of them. So let's take the second one first, which is the one down here. Let's be greedy. I'm a branch. I want to win the choice. I try to get the lock first, and the other one too. So we compete on the lock. And let's see where we get. So we grab the lock first, and then we try to consume a message. And let's put that in a context where this branch here actually could succeed. Now, this is concurrency. So the first branch might be quicker, and we end up in a situation where the first branch is blocked because apparently there is no message for it around. There is no message on channel A. And the other one, the second branch, which could actually consume a message, is blocked by not having access to the lock any longer because it lost in the first place. So bad idea to choose this order. So let's take the other order. And that is what we did in the end. So we have the lock, we have our two branches. They first try to consume the message. Both of them have messages there. Let's consume them. Let's both consume them. It's concurrency, right? They can do that. And now they compete on the lock. Let's have the second one win. And we end up here. So that would basically mean the second branch may proceed. But the first branch, well, it's actually done something to the environment. It's done something to the system. It consumed the message. And that is meaning we changed the overall behavior. So we somehow need a way to get this message back to the system. And that would need Q to tell the remainder here, you have actually lost. And that's why we put back the lock with a different state. And now let the other branch consume this and free back the message that it once consumed. And now it's back there again. And that is basically the idea of the whole choice encoding that Benjamin and Dave had. And in what sense is this correct? And that is where the whole fun started. There is one problem. What does an observer see of that kind of choice protocol? Well, it sees actually that sometimes there was a message, it's being consumed, there was some computation going on, and then the message pops up. Because there was a choice branch that actually did not succeed, but it needed some time to find out that it actually would not succeed. So is this in some sense equivalent to doing nothing? And in standard weak bisimilarity, it's not, but in asynchronous bisimilarity, it is. Problem solved. And that goes back to work by Honda and Tokoro and by Amadio Castellani and Sangiorgi 5 years later, who did that on a standard transition system. I think I've seen Ilaria also in the audience. So this problem was solved, but there was a more severe problem, and that had to do with so-called partial commitments. So remember, we were in a situation where both branches had consumed their messages, and they were competing for the lock. In this situation, we know already that some branch will win, because they had messages at hand, they could actually proceed. They just need to argue for which of them. But we don't know that. And this kind of partial commitment pops up when you think about the correctness of that encoding. In essence, what you see here is a source level step for deciding a choice, and its implementation where we have this kind of intermediate state where a choice is actually pre-decided, but we don't know yet for which side. Technically, it means that in the beginning we have corresponding states, but this intermediate state with a partial commitment does neither correspond to the beginning above and the end above, which differ by only one step at the source level. So this kind of partial commitment was there, and now there are two solutions to the problem. First solution, there is a known equivalence, which is called coupled similarity, and it tackles precisely this thing. So it's going back to Parov and Judin in '92, and actually Rob had done some early axiomatic ideas in 1988. And then in the course of doing these choice encodings, Ole Jensen and Robin Milner actually rediscovered coupled similarity also, without kind of knowing it. So what does it mean? P and Q, as you see here in these two transition systems, they are not weakly bisimilar, obviously, because here is an intermediate state where you have different branching behavior that does not correspond to anything on the other side. So this step pre-decides for either B or C. There's no longer the choice to reach A, but it's coupled similar, meaning P and Q are coupled similar, and the intermediate state is okay. Second solution. We can manipulate our encoding and introduce something like a rollback or like an abort transaction. And then we get back weak bisimilarity for correctness purposes, but we introduce divergence in this encoding. And a couple of years later, Yushi Fu actually proved that what we only conjectured, you can actually not do it otherwise. So if you want correctness up to weak bisimilarity, you have to deal with divergence. So Yeah, and the title of the paper is actually Decoding. It's just about all the technicalities that in the long version go over 30 pages. It basically means that whenever you have an intermediate state, you can actually properly decode it back to the source level and say where in between it's to be situated. So what are the main contributions after all? Yeah, we have these two technical results. We have two encodings. One is non-divergent, the other one is, and we have coupled similarity as a correctness criterion and weak bisimilarity for the other one. What Rob also mentioned, these were one of the rare examples of direct comparability, which means that you can actually not distinguish a term from its translation directly. It's not going the deviation by full abstraction, where you say, whenever I have two source terms, if and only if they are equivalent, then also their translations. No, we can directly compare them and do that within a more or less standard notion of equivalence. Yeah, these are also both two asynchronous versions thereof. That was the technical contribution, but I think we highlighted back then the importance of coupled similarity because it always pops up in actually almost all encodings when you want to compare source terms and target terms, and you can actually say coupled similarity or a variant thereof is kind of a manifestation of operational correspondence, which like a simulation and co-simulation between source and target computations. And it's also always fitting distributed applications. That is also what was highlighted back then. And another contribution was maybe it showed that this base calculus in PICT is really incredibly expressive. And it's basically all you need for programming, for concurrent programming. And what we didn't know back then yet, sorry about that, it actually also satisfies a property that is called locality. And that is all you need together with asynchrony in order to get fully distributed implementations. So what is locality? That goes back to the localized pi calculus, which was then 2 years later after we did this work, done by Massimo Merlo and Davide Sangiorgi. And it basically only takes the base calculus that we were looking at for PICT and says, yeah, whatever you can do for with a received name is possible. You can send it on another channel. You can send something on it when you have received it, but you are not allowed to receive on it. And this kind of not receiving on a received name gives you a locality property, which is basically what you find in PICT and join and what was also popular back then, typed concurrent object-oriented programming in Taiko. And our choice encoding fits with this scheme, so we never use this kind of bad locality damaging property. So we didn't know at that time, but actually what we supplied with our encoding is actually implementable in a fully distributed way, and PICT was only a monoprocessor implementation doing concurrency. So to end this with a even larger picture, so this localized version that I just mentioned is on a different distributability level compared to the standard asynchronous pi calculus. And that actually has to do with what Petrinet people know as the M structure. And I know Rob was very active in that. So in essence, in a asynchronous pi calculus, you can express a structure where two actions or two transitions A and C that look independent because they do not share resources actually cannot be put on the same distributed location because there is another transition in between that connects these resources. So in the localized version of pi, we cannot express these M structures, and likewise not in a distributed pi calculus, and likewise not in the join calculus, and in the actor pi calculus, and in some version of mobile ambience. You can express these in a pi calculus with separate choices and in the standard mobile ambience, and you can even do worse things. If you have mixed guarded choice, then you can express even more synchronization patterns that we discovered as what is known as a star. And that is pretty much what you need in order to write down a dining philosophers program with at least 5 people. So most of that work is done by Kirsten Peters and in her PhD thesis. And the story would go on. I mean, there are N structures, and you can put that in context with multi-party session types, but I better stop here because I'm already over time. Thank you.
Thank you very much. That was wonderful. Are there questions from the audience? I see a hand. Can I see by whom? Nobuko, please ask your question.
Yes, so I would like to ask phi encoding. One of the important criteria is this: your encoding is fully distributed. Phi encoding is important, fully distributed, because there are also non-fully distributed encoding, such as joint calculus encoder, asynchronous pi calculus, crossing the bar, and also recently there is a mediator which uses, say, encoding like this, And so, can you comment phi encoding should be, it's better to be fully distributed?
It depends what you mean by fully distributed encoding, I guess. If you go, for example, from here to there, from the mixed pi calculus to the one down here, we can actually find encodings that do the trick, but they do not preserve distributability. And actually, in practical terms, this is mirrored by the fact that in order to solve a mixed guarded choice, you actually have to run some kind of consensus protocol, which is expensive. And things show up in several occasions like that. I mean, if you know the work by Katusha Palamidesi, she did some similar things that had to do with expressing at this level electoral systems, and then showing that any encoding under some assumptions of preserving reasonableness and fully homomorphic parallel composition would actually also allow to solve electoral networks down here, but then she showed that you cannot solve them here. It's like not having the star structure down here. It tells you that you cannot have these kind of encodings. But her notion of distributed encoding was a little bit more restrictive. So we have another notion of distributability preserving encoding, and that would apply to basically all of those. So if you have this notion, then you go back and forth at this level, and back and forth at this level, but not cross the border.
Okay, thank you very much. It's very clear. Thank you.
Yeah, thank you. I don't see further raised hands at the attendees. And maybe given the time, we should move to the next prize. Anyway, I will tell everybody that at the end of the session, there is still a quick opportunity to ask questions to all the panelists, including Uwe. In the meantime, this was an extremely enlightening expose, so thank you very, very much. The next block is awards for the period 96 to 99. As I said at the beginning, there were 2 blocks of awards that we do in one concur in order to catch up over the years. And in this period, again, 2 papers have been awarded. The first of those is a paper by Ahmed Bouyani, Javier Esparza, and Odette Mahler. The latter, unfortunately, no longer with us. The paper is Reachability Analysis of Pushdown Automata, Applications to Model Checking. That paper is a breakthrough that opened the way for the analysis of push-down automata via model checking techniques. The paper proposes a general class of alternating push-down systems and defines new model checking algorithms. Sorry. It defines new model checking algorithms against both linear and branching time properties. The basic idea is simple and extremely elegant, using regular automata and representations for sets of states of push-down automata. The paper proceeds to show that the representation is close with respect to Boolean operators, makes membership of states decidable, and crucially, makes the predecessor operator easily computable. The approach proposed in that paper is so neat and natural that it has become a standard reference in the field of verification of infinite state systems. I invite Xavier to give a presentation on this paper explaining its role in this field. Thank you.
Okay, thank you, Rob, for the introduction. So let me share. So I hope you are seeing my screen now.
I do.
Okay, so Ahmed unfortunately cannot be here today due to a serious family problem, so he has asked me to thank the jury on his behalf. And both Ahmed and I wanted to start this presentation by remembering our co-author, Oded Mahler, who, as Rob said, passed away 3 years ago, far, far too early. He was only 61. At some point, we met at some workshop or conference, and we were commenting how happy we were because this paper, which is the only one on which the three of us collaborated, was getting quite a nice number of citations. And then Odette made this comment: look at all the damage we've done. And I'm sure that if you have ever met Odette, you know, yes, precisely that's what he would say. So let's go back to 1997. By the way, this is an original slide from the time written by me around, I guess, 99 or 2000. It's not a deep fake. I can show you the original, right? This is really a physical object. And well, I find it interesting that, you know, in 99 or 2000, I didn't know that I would be squeezing juice out of this idea and Ahmed too for quite a few years to come. So what did we do? So we were working on this model of push-down automata, and you all know it. So we have a finite set of states or control locations, and a finite set of stack symbols, and then a finite set of transition rules that tell you that if you are in control state P and the top stack symbol is gamma, then you can, or the machine can move to the state Q, replacing gamma by the string of symbols W. And that's a non-alternating push-down automaton. And in the alternating case, what happens is that the rules have this shape. And this means now that if the machine is in control state P and the top stack symbol is gamma, then the machine can split into n copies, which go to the control states Q1 to Qn, replacing gamma by the words W1, W1. So one of these push-down automata, take this one, non-alternating, has a configuration graph. The one for this particular automaton is shown here. It is a fragment is shown here because it is infinite. And for example, this is the configuration which where the automaton is in the control state P and the stack content is D. So the idea that we propose in this paper was to use automata as a data structure to represent possibly infinite sets of configurations. So for example, here you have an automaton which is representing the infinite set of configurations where the push-down automaton is in the control state Q, and the stack content, the topmost stack symbol is a B, followed by an even number of Ds. So for example, these two configurations belong to this set represented by this automaton, and there are infinitely many others that are below. So the main theorem of the paper was that given an automaton A, recognizing a set of configurations, L of A, then it was possible to construct another automaton, let's call it A pre-start, such that the language of this new automaton, A pre-start, is the set of all predecessors, not only the immediate ones, but the set of all predecessors of the configurations represented by A. And moreover, crucially, A and A of pre-star have the same states. So actually you can obtain A pre-star from A by just adding transitions. Almost the same result holds for post, and the same result also translates to alternating automata. So in this, continuing with the example, so if we take the set of configurations represented by this automaton, then we can compute the automaton for the set of predecessors. So remember that the set of configurations contain this and that. So now the set of predecessors contains all these things, all these configurations over here. And we can obtain an automaton for this set just by applying what later was called a saturation procedure, which means that we add new transitions to the automaton, to the initial automaton, following a very simple rule, and we just stop when we reach a fixed point when it's not possible to add any transition anymore. And again, the same translates just to the case of alternating automata, essentially the same scheme. So, and in the second part of the paper, we show that once you have this in place, these procedures for computing pre and post start, then you can easily apply them to define model checking procedures for push and automata and for formulas of LTL. For this, you don't need alternation, or after introducing alternation for the alternation-free new calculus. So, okay, so now 25 years later, why was this quite successful? Well, so I think there was a combination of actually 4 points. So the first one was that both the model and the saturation algorithm were easy to understand. So everybody knew push and automata, so you didn't have to really spend much time understanding the model. And the saturation algorithm, you know, actually the saturation algorithm, we will see later, even goes back to Vichy. When I arrived in Grenoble, when we were working together on this, actually, Ahmed and Oder had already proposed the algorithm. So it is actually their merit. And I was flabbergasted. I found it immensely beautiful. And I think that this actually is what many people have also experienced with this. And then it came at the right time, because at that time, infinite state model checking was emerging as an area. So Rajiv and David Dill, Rajiv who is here, in '94 had introduced time automata, which was a model with an infinite state space, but where you could still do model checking. And there were also results for Petri nets. When they are unbounded, they are also infinite state models. There were results also for fragments of process algebras. So from a theoretical point of view, there were already a collection of techniques that was starting to take shape. And what was also, I think, important is that in the early 90s, saw the boom of symbolic model checking using BDDs in hardware. So actually some people jokingly were saying that at that time, the CAF conference was the BDD conference because everybody was doing BDDs at the time. But this means that the idea of using symbolic data structures to represent, in the case of BDDs, large sets of configurations was very well understood. And when you see that a little change in this idea, because, you know, BDDs you can see as acyclic automata, now you consider automata possibly with loops. When you see that this change allows you to apply, to do something in also in another infinite state model, then also that everything falls in place. And yet I have to say, I think that this would have been enough to give this paper some number of citations or to be used by theoreticians. But actually what I think was the most important fact of all was that a couple of years later, so the paper appeared in '97, and in the early 2000s, model checking was moved from hardware to software. So by the end of the decade, everybody was doing software model checking. And in particular, there, of course, the SLAM project of Tom Ball and Sriram Rajamani was very, very important. So software is more structured than hardware. It presents many features like procedures and recursion and thread creation and locks and context switches and higher order functions. And all this, in order to do model checking for programs with all these features, you had first to model them, introducing usually automata theoretic models, right? And this was giving many opportunities to extend our results. So which was the damage that we did? So the paper, we were very lucky because it was alive for a relatively long time. So usually, you know, the number of citations to a paper goes up and then it goes down. And in this case, it had two kind of revivals. So it reached a first peak here, and then it reached a second peak here, and a third peak here around 2013, and then it went down because there were many papers that it had been superseded by many works. But it lasted so long because the result could be extended in quite a number of ways. So the first idea was to try to not, I mean, the paper presented theoretical algorithms, but they had to be transformed into efficient, really, algorithms and working out the complexity and the data structures to do this. And this led to actually a tool developed by Stefan Schwan in his PhD thesis in Munich, Moped, which was quite successful, and I think very important for popularizing the results. And then Tom Reps got interested also in applying this to interprocedural program analysis, for which it was really essential to move the techniques from push-down systems to weighted push-down systems, where the transitions are labeled with carry weights from some semi-ring. And this led again to an implementation by Stefan Schwan and Tom Reps, and I think Sumeshia was also involved, and Melsky, which was actually also very, very successful. And it led later, by generalizing the kind of semi-rings you can deal with even more, to work that we did in Munich on Newtonian program analysis. I think, which is again maybe more theoretical, although Tom Reps was also making quite a bit of use of it, but I think it was a very nice development. So then many other people, I'm sure I am forgetting many people. So for example, Luke Ong and Matthew Haig and his supervisor Luke Ong managed to extend the technique to the full mu calculus, something that we didn't know how to do. We tried, but failed. And for example, Igor had given some techniques for push-down games, also using other techniques, but later on, Thierry Cachat or Parash Abdullah were able to apply our saturation algorithm also to the problem of computing winning regions of push-down games. Another large block of work were concurrent programs with procedures. And this led actually to quite a few notions that were introduced and became very popular. So the idea, and the problem was, of course, that if you just take procedures and concurrency without restrictions, you put them together, you get an undecidable model. So you get that programs with only Boolean variables, so you can have a class of programs with only one Boolean variable, but still model checking this class of programs is undecidable. So you have to introduce different kinds of constraints in order to come back to a decidable problem again. And many were introduced throughout time. So bounded context switches by Kadir and Rehov, or Kalon was working on locks and nested locks. Ahmed was working on dynamic pushdown networks with other people, and then other models also appeared. And then even further, I mean, this was already enough. We were really surprised that this had been taken so far, but there was even further work on how to extend the techniques to higher order programs, to programs where, if you want, procedures can be given another procedure as parameter. And this was done by extending the model of push-down automata to collapsible push-down automata. And again, many people will work on that. And it was also possible to extend the models with time and probability. And even more, I mean, Ahmed did quite a lot of work on expanding the methodology of applying finite automata as data structure to represent infinite sets of configurations of other systems. And this led to work on FIFO channels or to regular model checking. And the slide which is fundamental here is to say, well, I have presented the work that was coming, or that you can trace back at least partially to our paper. But there were other techniques, let's say our competitors, other techniques which were proposed in parallel with ours, which also were very influential and probably even more influential than we were. First, it's important to say something about the precursors. We were not the first to invent the saturation algorithm. Actually, it goes back to Buchy, who introduced regular canonical systems, and you can already see, of course, a slightly different way of presenting it. And many other people, for example, Berhan Steffen and his group did work on context-free processes and push-down processes and model checking for these processes, but then not using this idea of symbolic model checking. Pierre Volpert and his students, Boisgelot or Godefroy, they did lots of work also on automata's data structures, in particular for Pressburger arithmetic, and the work of Molnar has to be also mentioned there. And then, you know, there was a competitor model, so to speak, an equivalent model, but which emphasizes other aspects, a competitor of push-down automata, hierarchical and recursive state machines. And Rajiv was a fundamental figure there, and he introduced, together with other people, lots of notions that are classic notions today, like the idea of computing summaries, or the logic for calls and returns, visibly push-down languages, nested words, all came out of there. And then when hierarchical and recursive state machines were extended with probability, though they became recursive Markov chains, again, a model equivalent to probabilistic push-down automata, on which Kusha Etesami and Michalis Giannakakis did lots of works. And higher order recursion schemes became also an alternative to collapsible push-down automata. So as you can see, actually, quite a few things came out of this, and of course we are very proud of that. And and in particular, we of course want to dedicate this to the memory of Odette, who started it all. So again, so thank you to the jury in the name of Ahmed and in my own name, and thank you for your attention.
Thank you very much. That was very clear and beautifully explained. Are there people that want to ask a question about this? If not, maybe I will ask one general thing. Do you think that the push-down automaton is one of the essential things to get the right balance between, if you do model checking, between generality, expressiveness, and decidability? Or would you say that the push-down technology is just one of many things, and there are candidates that are equally good or better now?
It is one of many things that you need. Of course, you cannot do just model checking only with push-down automata. You need many more things. But I think it's a kind of golden standard. So in the area of infinite state systems, it is one where everything fits. So it's not only decidable, you even have efficient algorithms which run in polynomial time, and that can be implemented very elegantly. And then when you start moving into more complicated things, then things start to fail, right? So this aspect does not work that well, that aspect does not work that well. You also see this when you are dealing with finite automata, right? So finite automata is a kind of gold standard, And then you have to generalize them, otherwise there is not so much you can do in many circumstances, but you always lose something. So it's like you always would like to go back to paradise, right? So this has happened to me all the time when we were extending the work.
I understand. Anybody else with a question at this time? If not, we better go on with the last presentation. Of course, time is not with us either. Thank you very much, F.J., for this wonderful expose. I will go to the last award, the one that's also in the period 96 to 99. And that's for a paper by Rajiv Allur, Thomas Hensinger, Orna Kupferman, and Moshe Vardi, alternating refinement relations. Many of the authors, in fact, all of the authors are here in the audience, and it's Orna that will soon give us a talk. I will first tell you about the paper. It introduces refinement relations based on simulation and trace containment for games modeled as alternating transition systems. Refinement relations had been a foundational notion in formal methods, and much more broadly in the theory of computation. In the years leading up to the paper, it had become evident that games provided a natural model for open systems which communicate and are reactive to their environment. This paper extends the notion of simulation and trace containment to games. While conceived in a formal methods and verification setting, the paper turned out to have broad implications, as these game refinement relations have implications for strategies in general games and are closely related to notions of subtyping in game theory and in dynamic typing. The extension of refinement relation to games was thus a fundamental test for the understanding of dynamic systems finally being put in place. Orna, please tell us more about this work.
Okay, so thank you very much for the introduction and for the award. And indeed, this is joint work with Rajiv Allur, Tom Hensinger, and Moshe Vardi. They are all here, so I will be short, so they will be able to talk too. We did it in '98. By then, I was a postdoc of Tom in UC Berkeley. Rajiv and Moshe were already in UPenn and Rice. We now moved. Okay, so as you can see by all the talks we have so far, yes, so refinement was a very popular topic in '98 and at the late '90s. In refinement, we have two systems, system AI, and we say that it refines system AS if AS has more behaviors than AI, and it's good to think about AS and AI as a specification. This is also why we call them AS and AI. So AS is a specification. It has many behaviors. It just gives an idea what the property that the system should satisfy is. And then AI, the implementation, is less abstract. This is also why it has fewer behaviors. And we want indeed that every behavior of the implementation exists, is allowed in the specification. And what do we mean when we say behavior? So that was another very popular topic at the late '90s, because when we say that AS has more behaviors than AI, we can either take the linear time approach or a branching time approach. In the linear time approach, having more behaviors mean having more traces. So AI is a refinement of AS if every trace of AI is allowed in AS. So refinement is reduced to trace containment. If we follow the branching time approach, then we want every tree that exists in AI, that is embodied in AI, to be a tree also in AS, and this is called simulation. And many work about trace containment and simulation, they differ in their definition, in complexity, logical characterization. So the definition of trace containment is global. We talk about whole traces of the system. In simulation, the definition is local. It relates states and their successors. Accordingly, the complexity of trace containment is higher. It is p-space complete. Simulation we can check in p-time. And the logical characterization also related to Igor's talk. So in trace containment, if a system is contained is trace contained in another system, then we know that every LTL formula that is satisfied in the first is satisfied also in the second. If we are in simulation, then we can say the same about universal CTL star, universal CTL, and we know that model logic is sufficient. So different properties for trace containment and simulation. And simulation is stronger in the sense that simulation implies trace containment, but not vice versa. This is the popular example by Milner. Yes, so we have here two systems, AI and AS. You can see that they have the same set of traces. They can generate ABC or ABD repeatedly, but they don't have the same structure, the same tree structure. So AI is trace contained in AS, but there is no simulation, a tree in which B can merge, can branch to C and D exists only in AI. And if we want to use the logical characterization, or we often call it distinguishing power, then indeed we have a formula in all successors satisfy C, or all successors satisfy D. It is satisfied in AS and not satisfied in AI. Indeed, there is no simulation. So these were two first things that were very popular in '98, and another topic that emerged there is the issue of closed as opposed to open systems. So an open system is a system that interacts with its environment. So now when we talk about the components of the implementation and the specification, we care about their behavior in the context of another component of B, the environment. And the question we want to ask is whether AI refines AS in that context, in the context of B. So what does this mean? AI refines AS in the context of B. Essentially, we want to formalize the fact that every behavior that AI can enforce in the composition of AI with B can be enforced by AS in its composition with B. And this is different from just asking whether the composition of AI and B refines AS with B. Why is it different? It is different because if we look at the joint behavior, then it's the collaborative behavior of them. And what we really want, and this will become clearer as I keep talking, we want the behavior of A against B. We don't want, for example, the behaviors of AI and B to be contained in these of AS with B because AI disallow some inputs and things like that. So this is our contribution, alternating refinement relations, something that will take the very popular issue of refinement and put it in the framework of compositions. And in order to talk about alternating refinement relations, we should talk first about the model that is used. So in the case of closed system, when we talk about trace containment and simulation, the model was transition systems, which are flat, so we will get to it. In alternating trace containment and simulation, we talk about systems that represent games. We call them alternating transition system. That's a previous work. And the issue is that the main idea is that if we look at the composition of two components, A and B, and we don't want to look just at the collaborative behavior of them, then we can view it as a multi-agent system or as a game arena. I will define it. So let's first recall what is a transition system. This is something you know. So we have a set of atomic propositions, set of states, initial state, a transition function which is non-deterministic. So delta is a subset of S cross S, which means that a state may have several successors. And we have a labeling function. Each state is labeled by the set of atomic propositions that hold in it. This is the model over which we define, right, the trace containment and simulation for closed system. Now, what is an alternating transition system? We have almost the same components, but we add two components, omega and Ci, and the type of delta is different. So AP, S, S0, and tau, they are as in transition systems. Omega is a set of players. Let's assume they are K players. Then the CIs are sets of actions for the players. So C1, for example, is a set of actions that player one may choose in each state. And then the type of delta is that given a state and actions of all players, we have a deterministic successor state. So these are alternating transition systems. The main idea is that while in transition systems, that was the type of delta, pairs of states, now delta takes a state and actions for the players, and the actions for the players deterministically tell us what the next state here is. Here is a small example. Yes, suppose we have a K is 4, we have 4 players, oopsie. So delta takes a state and actions for the 4 players and determines the next state. If we are in S0 and each player determines what her next action is, then the next state will be delta of S0 with these 4 actions, and the interaction between the players move to the state S1. So this is how alternating transition systems model multi-agent systems. And once we have this basic definition, we can talk about strategies for the player. So a strategy for player I is something, Fi, something that tells the player if the history of the game so far, just a moment. So which action the player should choose if the history of the game so far is some sequence of states, right? So this is the strategy for player I. Then a profile is a vector of strategies for all players. And once we have a profile, we can talk about outcomes. So the outcome of a profile P from state S, this is the single computation of the system when the game starts at state S and the players follow their strategies in P. And this is indeed a single computation. It is S0, S1, S2, and so on, such that we start with S, right? It's the outcome from S. And for every point in time, for all j greater than 0, the next state, Sj plus 1, is the single state that delta maps the previous state and the actions that the players provide according to their strategies. So we have strategies and we have outcomes of profiles of strategies. And once we have these definitions, we can talk about the ability of players to force behaviors. So what do we mean by players forcing a behavior? For a set of players A and a state S and some desired language L, we will say that the players in A can force S from the state S if they have strategies, if there are strategies Fi for all players I in our set A, for the players in A, such that for every profile P in which the players in A follow these strategies, the computation that is the outcome of these strategies is in L. So the players in A can force L from S if they have strategies such that no matter what the other players are going to do, the outcome of the interaction is going to be in L. And for example, here one player can say, if I choose A4, then no matter how the other players proceed, the next state will be labeled P. So this player can force the language next P. And now, what is the definition of refinement in a context of an environment? So AI refines AS in the context of B. Again, we can talk about the linear approach or the branching approach. In the linear approach, AI in the context of B is A contained in AS in the context of B. So note that we now have a parameter of who are the players we care about. And this happens if every trace that AI can enforce in AI with parallel with B can be enforced also by AS in AS and B. Note that I refer here to AI, right, as a set of players because it is a component. So this is the linear time approach. And in alternating simulation, it's the same, only that we talk about a computation tree. But in order to make it clear what's exactly going on, let's compare alternating simulation and simulation. Yes, what's the technical definition behind it? So recall that in simulation, if we want S0, take this back, S0 and W0 to be a pair in a simulation, if we want every behavior in S0 to be possible also from W0, then our definition says that every successor we take from S0, there should be a successor of W0 that is labeled in the same way. So this is how we define simulation, and this also induces a game between two players, an OR player and an AND player. And the OR player has a strategy to proceed forever. Yes, the AND player is moving the token in AI, so it generates a trace, but it generates it in a local way. That's the difference between trace containment and simulation. And every step that the AND player chooses, where she moves the token, the OR player moves the token in AS. And if she's able to do it forever and along the play, the labels are the same, then we say that AS simulates AI, and there is simulation relation between them. That's in the case of closed system. In the case of alternating systems, alternating transition systems, how do we define alternating simulation? So now it goes like that. First, the AND player chooses actions for A in the implementation. The implementation along with its context. So the AND player, the player that wants to claim that there is no simulation, she chooses actions for A in the implementation. Then the OR player chooses actions for A in the specification. Then again, the AND player chooses actions, but now for the other players in the specification, which gives us a successor. And now the OR player chooses actions for the other player in the implementation, which gives us a successor, which should satisfy the facts that it is labeled as the successor in the specification. And if you think about it, you will see that this is really what we want to say. We want to say that every tree that the players in A can enforce in AI with B can be enforced by them also in this composition. And now you can also understand why it is called alternating simulation, because, right, the players alternate turns in order to check that simulation exists. So these are alternating simulation and trace containment. Again, we have this game formulation. And if we compare their properties, so that was the picture we had in the flat case of trace containment and simulation. Now in the alternating setting, it's almost the same in the sense that, again, the definition is global versus local. The complexity of alternating trace containment is higher. It jumps from P space to X time, but we are not surprised because we know that usually alternation takes us higher from P space to X time. For simulation, we stayed P time because everything is still local. And the logical characterization, it used to be LTL and CTL. Now it moved to alternating temporal logics that have past quantification that talks about the ability of agents, of players to enforce behaviors. So this is the picture we get. And to sum up, so our contribution, first we formalized alternating refinement relations. We studied them in different settings. So the alternating transition systems, they may be turn-based, they may be concurrent. We described algorithms for deciding whether there is an alternating relation, and we gave a local characterization. So these are the technical contributions, and a more general contribution is that we have a bridge between formal methods and game theory, which became stronger in the years since then, right? So we have a lot of work that relates formal methods and the challenges we have with these that exist in game theory. And this is it. Thank you.
Thank you very much. That was very clear and wonderful. Is there anybody who wants to ask a question? Please raise your hand by clicking the token on the bottom. I can, in the meantime, there is a question by Igor.
Yeah, thank you very much for the talk. When looking now at the talk, I realized there is Tabuada in control theory has introduced something exactly with the same name. Is it exactly the same thing, alternating simulation, but restricted to dynamical systems in control theory? Do you see relation with?
So what was it?
It's Tabuada in control theory. They have alternative simulation. So this is a relation that couples a dynamical system that is continuous with a discrete system. I think Rajiv wrote a book on this. So
I'm not familiar with it, but I know that there are many similarities between things that we do and things that people in control theory do. So it may be perhaps.
It's the same thing. I mean, you know, he was at Penn, and you know, he just. I mean, it's a follow-up work.
Okay, so he knew about your work.
Same definition, but you know, applying it to the dynamical system.
Yeah, this is what I realized now when looking at the talk. I know both things, but I kind of Thanks a lot.
Yeah.
Thank you. Benoit, at your end, there is a question.
Yeah, it's rather me that I want to make a comment about this talk, because we are actually reading this paper now, and for research we are doing it. And there is something that Orna said about open and closed system that I was curious about, because in fact the simulation by Milner, which she says is for closed system, but in the setting of CCS and process calculate, they are open systems, and by simulation is actually a congruence, because you compose with other part of the system. I find interesting that these two different soul of Concur, the more syntactic one by Milner and the more say automata oriented part, use the notion of simulation in different ways. So I don't know if you want to comment, but Milner uses simulation for open system, in fact, and you say that simulation is for closed systems. And I found that interesting. It's not criticism at all. It's just different soul of Concur that use terms in different ways.
So Tom, I feel.
Can I mean, I feel like can I jump? I mean, our simulation is exactly Milner's simulation, and Milner's simulation is in fact for a closed system. In fact, I see Rob here, right? Who wrote the work on all these, comparing all these refinement relations for process algebras. It really puzzled me in the 90s that these they went to great lengths of capturing the environment. You know, there were notions of ready simulation, and I forgot most of these. But I mean, what alternating simulation does is simply making inputs and outputs dual, but symmetric. You know, an implementation can restrict the outputs, but it cannot restrict the inputs. It can enlarge the inputs. The implementation must implement every input that's allowed by the specification, but it may restrict the outputs that it implements, and it's simply making the things dual, and it's exactly based on Milner's simulation.
Okay, thanks. It's interesting to have this point of view because I never thought about that in this way.
Yeah, I also think it's quite interesting, and different cultural sub-communities of Concur, things are done slightly different, and there is a lot of applications of simulations and biosimulations in Milner's sense that are fruitfully used to reason about open systems in some way. I think it depends on how you model them and what aspects that you want to capture, but this dual interaction that's captured by the alternating simulation is really the one that shows this interaction in a very beautiful way. I have one more question. There is a lot of modern work on concurrent games. Concurrent games seem to have increased enormously in popularity since that paper was written. And I cannot say that I really kept up with all the literature, but I know there are quite a lot of innovative, different ways that games can be organized. And are there alternating simulations still the right tool for the concurrent games that are nowadays applied? It's a bit of a fake question, but I'll just
so I can answer what Rajiv, Moshe, and Tom. Do you want to? So,
go ahead.
So I think that one thing that we see in the last years is that people care less about zero-sum games and care more about non-zero-sum games. So in zero-sum games, we have a system with an objective and then an environment whose objective is dual. In non-zero-sum games, the system and the environment may have objectives that do not conflict. And for that setting, we need different mechanisms or different definitions. It's not alternating simulation as we do it, because alternating simulation really assumes duality, complete duality between the system and the environment. For that setting, I think that yes, I think that alternating relations capture what we want, but for richer types of games, in particular non-zero-sum games, we need different relations.
That's a very illuminating perspective. Since we are actually 10 minutes over time and getting to the end of the meeting, I'd like to open the floor for few quick questions that people may have to any of the panel members that are a part of this presentation. So all the 4 prize-winning papers could be the subject of a question if somebody has thought of one in the meantime that they still want to ask.
I think Nobuko wants to say something about the interview that where.
Yes, that would be a very good thing to do. Shall we first go to Igor's question online and then give the floor to Nobuko?
Okay, if I can, it's maybe a bit technical, but I have a question to Uwe in the meantime. He talked about M and N structures in Petri nets. So Petri nets without N is series parallel, as I understand, more or less. But Petri nets without M, is there any characterization like compositional syntax for such Petri nets or anything? Do you understand it well? What are the Petri nets without M structures?
As I'm not working on Petri nets myself, but I know that Rob did quite a lot of work on anything having to do with what is implementable in that sense. I would rather pass on to Rob.
Okay. In my understanding, which is maybe not up to date, I do not know of a syntax, some kind of subprocess algebra that generates exactly the M3 Petri nets. So in that sense, I say no, I do not know. as far as implementability concerned, I know of quite a few case studies of systems that use PatriNet, and it's very common that things can be implemented in an M3 world. So much more than the series parallel PatriNets, which are theoretically interesting, but of limited practical significance. I think the ones without M are of great practical significance, as almost all practical problems you encounter in data life can be brought with some effort into this class.
Thank you very much.
Are there no concluding further questions? Then I pass the floor to Nobuko about
Yes.
the
Interview article to winner will be published in EATCS Bulletin, October issue, and so please have a check. Thank you very much, Luca and Nathalie.
That's very good to know. And there are some interviews already available also in the process algebra diary of Luca, either directly or to reference. You can just find them by Googling process algebra diary of Luca Aceto. I think this will be the end of this session. I thank all the panelists for their insightful contributions and all the audience for the questions and helping this celebration be a success. And it's the end of this day of Concur. I might see some of you later in the week. Thank you very much and goodbye.
Thank you, Rob.
Thank you, Rob. What time is it for you?
It's for me 3:44 a.m.
So thank you very much again.
Time to go to bed.
Bye, bye, bye.
Bye, bye.
Okay, bye.
Bye.